the talk is consequences of the axiom of choice, most of which we like, consequences of the negation of the axiom of choice, most of which are pretty bizarre. But at the end, we're going to see some really crazy things. So to begin, this is a short list of equivalent conditions. Last time I brought a prop. It was a book, like a 400-page book. There was nothing but equivalent conditions to the axiom of choice or statements that imply the axiom of choice. But that book was totally unreadable. And if I ever look at it again, it'll be too soon. But you can write, people write entire books on statements equivalent or slightly weaker or slightly stronger than the axiom of choice. And they're not books, they're just lists of things that are similar to the axiom of choice. So this is the most important one, probably, called Zorn's lemma. I'm not going to explain what these words mean, but every chain in a partially ordered set has an upper bound, then the set has a maximal element. You use this to prove the hung by theorem I just mentioned. You also use it to prove that every vector space has a basis. It's very important, but I think far less intuitive than products of non-empty sets or non-empty. And there's a really fun quote from this guy J.L. Bono that maybe some of you have heard before. The axiom of choice is obviously true, the well-ordered principle or theorem is obviously false, and who can tell about Zorn's lemma, right? And this is certainly how I think everybody feels about these things. The statement of the axiom of choice is so obvious that it's hard to imagine today why anybody would object to it, but then the well-ordered theorem, which it was really invented to establish, seems totally outrageous. So what the heck is the next decimal number after E? And then on the other hand, Zorn's lemma, which is equivalent to both of them, we have no idea. I mean, what does that even say? Every time I read this, even I have to scratch my head and remind myself really what this means. I do not see the connection between this and the axiom of choice, to be honest.
But do you see the connection to the well-ordered principle?
I think...
Or not maybe the principle, but orders.
Yeah, okay, that's more obvious, yeah. But I mean, I would never in a million years look at this statement and identify it as being equivalent to the axiom of choice. So the next equivalent statement is really just a statement of the theorem in the axiom in topology. It's called Tychonoff's theorem, and I put theorem in quotation marks because it's also just equivalent to the axiom. It says that the product of compact spaces is compact. This is a nice topological thing, and I only mention it because someone did a meta-study of every journal in mathematics, and they found that this was the most cited theorem in all of mathematics. And that doesn't mean exactly what you think it means. It means that it doesn't mean it's the most used theorem. It's the theorem that's most used that is also complicated enough that people feel the need to name check the result and not just implicitly assume it, right? Because really obvious things, you don't bother saying, by obvious statement A, therefore this.
So, the associativity of addition.
Oh yeah, exactly. By associativity of addition, A plus B plus C, it doesn't matter how you bracket it, right? I mean, this is very obvious. So Tychonoff's theorem is the least complicated thing that's still complicated enough that people felt the need to write down the name every time they use it.
It's the successor of all the obvious statements.
Exactly, it is the successor of all the obvious statements.
Because obvious statements have a well-ordered.
Well, everything does, right? Because we all believe the axiom of choice. So I think the next one is probably the basis one. Yeah, every vector space is a basis, and the cardinality of any two bases is the same. If you're into linear algebra, then you probably like this result. Vector spaces are kind of like coordinate systems. So vector spaces are things that are like space, although they might be infinite dimensional. And really this is saying that every vector space has a coordinate system, and you can't have coordinate systems where you need different numbers of coordinates. That would be truly bizarre, right? So that's what this is saying in kind of the normal English language. And I hope I have one more because there's space for it. Ah, yes, maybe the most important one, the trichotomy of cardinals. So if you give me any two sizes of things, one of three cases should be true, right? One of them, either one is smaller than the other, they are the same, or one is bigger than A. This, I think, is maybe the most obvious statement that we've seen. Like, how can anybody dispute this? Give me two sizes, one of the two is the bigger size, right?
Do you need this? Do you need the choice to prove that for just finite cardinals, or are you talking about infinite cardinals?
Finite things, you just count them, and the bigger one is the bigger one, right?
So it's really infinite cardinals where this becomes important?
Yeah, so all of these statements they're kind of for all statements. They're saying for every such thing. And you only need it for infinite dimensional vector spaces if you need this statement.
Right.
And then you only need this for infinite cardinalities, right?
Right.
If you're happy living in a purely finite world, you never need any of this choice nonsense. It's only once you start dealing with infinite things that you need this axiom of choice. But really, you almost can't do anything without the axiom of choice once you're allowing infinite things to exist. So, I mean, does anybody dispute this? I'd be shocked. How can anyone disagree with this statement?
The last statement?
Yeah.
I mean, like the last statement, seems obviously true only because you're being tricked into thinking about finite cardinals, right? Like, there's no reason to believe that that's true for infinite cardinals at all.
Well, okay, fine.
Like, I mean, I was at your talk where you talked about
Yeah,
cells
okay.
of infinity. I understand
Yeah.
why we think that, but there's no reason to think that that's obvious.
That's true, yeah. You have to be very careful with your intuition. All of our intuition comes from the finite world. You know, I've only ever seen a finite number of bananas. So like, I can't reason about infinitely many bananas, really, not at all. And there's this easy examples like this Hilbert's Hotel that already has crazy problems. So this is the correct attitude. Aaron?
So, sort of inspired from the cardinal thing,
Yeah.
is there any relation between the axiom of choice and, say, measures that aren't real? Like imaginary measures or something like this? Or, sorry, measure spaces that have, I don't know what you call them, but
Complex
complex
measures,
value
yeah,
measures. Because essentially the cardinal, I know it's not a measure, but it's this would imply that the cardinals exist in some set that don't have an ordering, essentially.
Yes. Yeah, this is exactly the problem. If you can well order the cardinals, then you're done.
Yeah. So I was curious.
We are going to see a connection with measure theory shortly, but it's not the connection we're looking for.
Okay.
I'm not sure what the answer to your question is, but we should talk about it.
Like, yeah.
Okay, so this thus concludes my list of equivalent conditions to the axiom of choice. And I think they vary from pretty obvious, at least if we allow ourselves to abuse our intuition from the finite world, to totally outrageous, like Zorn's who knows what that's saying. But I think at least the later ones are believable, even the complicated topological ones, if you've seen enough topology to understand what I mean. So, the first weird example of something that happens without the axiom of choice is this result. I did this last time on countability. So
Is this without the axiom of choice or with the axiom of no choice?
well, yeah. So, this statement is fine as is.
But the thing you're going to
I'm going to negate the axiom of choice and see what happens,
Okay.
but I'll be explicit about this. So we've mentioned this already. We call a set countable if its cardinality, if its size, is the same as of the natural numbers. This is the smallest kind of infinity. And every undergraduate who's exposed to this idea in second or third year will be asked to prove this result, that the countable union of countable sets is countable. And I guarantee if I went to any undergraduate mathematician at Waterloo and asked them, is this true? They'd say, of course, and they'd give me a proof. They'd probably give me the standard proof. So it turns out this result actually fails without the axiom of choice. Without the axiom of choice, you can prove that the real numbers, which is your prototype for non-countable set, can be written as the countable union of countable sets. So this was new to me when I was preparing this talk last time I gave it in December. And this really offends me on a visceral level. Like, I'm fine if you want to disagree with the, weird non-constructive existence of these choice functions or product things, but I refuse to live in a world in which this is true. So this is why I am not okay with Russell's constructive nonsense.
Well,
Yes?
in the constructive universe, R has the same cardinality as N, right? So
No, you can, R is always a strictly bigger cardinality than N. Cantor's original diagonalization is totally fine.
not in constructive mathematics, though.
Okay, that's not my understanding.
Also,
I could be right.
Projection.
The issue here is that the countable union of countable sets is no longer countable, not that the reals are countable. I don't see how the reals can be countable.
Well, in constructive, that's what if in constructive mathematics you have the constructive reals, which is a countably infinite set.
I guess in the diagonalization you're using excluded middle. Is this the issue?
Yeah, that's right.
Okay. And if you don't allow this, you show that the reals are countable. Well, to me that's equally upsetting. So, to me, excluded middle is not even up for debate. If you want to debate whether or not the axiom of choice is valid, then that's one thing.
Yeah, but if you don't have excluded middle, if you don't allow excluded middle, then axiom of choice may or may not be false. Like you don't necessarily have this condition where it's either true or false.
Okay, yeah.
So this problematic statement here is you are forced to swallow this statement because you want excluded middle.
Yeah, right. Well, okay, yeah, I guess it.
So it's your problem.
Okay.
Someone needs to be true or false.
I guess we should discuss this after. Yeah. This, at least with excluded middle, the reals will never be countable. I could see how if you don't allow proof by contradiction, then the diagonalization proof would not go through. But I still don't know how you prove that the reals are countable. Do you know a proof of this?
Well, I'm not a mathematician, I'm a computer programmer, and The constructor of reals is basically the set of all real numbers that you can write an algorithm to compute.
I think this is maybe different than my real numbers.
Well, yes, it is.
Yeah.
Exactly, because you're not a constructor
Oh, I see.
mathematician.
Okay. So I mean, I claim that we're discussing different results. Yeah. But we'll talk about this after.
Yeah.
So I'm still wondering about the difference here between without choice and with no choice.
Okay, so this is saying that if you don't assume the axiom of choice, then you can come up with a weird universe of sets in which this happens.
But you don't have to add the axiom of no choice.
I'm not saying, no, I'm not, well, I mean, it must be a weird universe in which choice fails for this to happen, but I'm not assuming the negation of choice. I'm just saying, without choice, this might happen.
So without choice, it might happen.
Or maybe not.
Right, okay.
Because there will be lots of different models, whatever
Right.
they call them, of set theory, in which choice is true or not. You see
Yeah.
what happens.
Cool. Okay.
So like, it is possible that this happens if you do not agree with the axiom of choice. I'm not assuming the negation. I will at some point. So there's also this notion of Dedekind infiniteness and finiteness that I'll talk about very quickly. So we call a set Dedekind or D infinite if it has the same cardinality as a proper subset of itself, so the same size as a proper subset of itself, which is really a purely infinite phenomenon, because if you take any finite collection of things, if I remove some of them, what I'm left with is strictly smaller than the whole thing, right? So nothing can be, no finite set can be in one-to-one correspondence with a subset of itself. But there's this famous Hilbert's Hotel example where you have an infinitely large hotel. There's infinitely many rooms, and every room is full, and you number the rooms. And then someone shows up to the hotel and says, like, I would like to rent a room for the evening. And the concierge says, well, every room is full, but I'll just ask every guest to move to the next room, whose number is one more than the room they're in now. And all of a sudden, room 1 is available, so you can move into this room. So in this case, it's possible that this subset, every room that is not the room number 1, is of the same size as every room, ever, including 1. So this is really an infinite phenomenon. So this is a nice definition of infinity that is not just saying not finite, right? This is a more constructive definition of infinity of choice. And weird things happen with the axiom of choice. If you're interested in this notion of finiteness, you can have D-finite unions of finite sets, which are not finite. The power set of a finite set, that's the collection, the set of all subsets. The set of all subsets of a finite set might be infinite. And the image, this is the most offensive one, the image of a finite set may be infinite. So you have some kind of finite collection of things, you apply some function to it, and somehow the function has infinitely many values, even though it only has finitely many inputs. Like, it seems totally ridiculous.
I'm guessing that the proofs for these are going to involve non-constructive mathematics, though.
Well,
I'm guessing. I mean, you're not showing how those results are affected.
I mean, I don't recall the proofs of these, or even if I've seen them, to be honest. But I mean, I don't know. I mean, they could not be constructive. The notion of, I say infinite finite, but this is really kind of a different notion.
Okay.
And it just might be that you fail to recognize that they are finite or infinite in a more naive, intuitive sense. I'll look up the proofs of these guys.
Could be a weird thing where the model is missing some functions that you expect, right? So they have the same cardinality or don't have the same cardinality.
Yeah, they should. Yeah, they might even have the same cardinality, but this weird finite business. You might the function that is the bijection between the subset and itself might just be missing.
Yeah.
To show that it is infinite. So weird things do happen like this. There's a countable model of set theory, for example, because it's missing bijections. Okay. So then this is kind of a summary of the disasters that can happen with the axiom of choice. And there are families of non-empty sets whose product is empty. This is just exactly the negation of the axiom of choice. So if the axiom of choice is not true, then there must be at least one family like this whose product is empty. This trichotomy of cardinalities fails. You give me two sets. I can't tell you that one is bigger than the other or that they're the same. Vector spaces might have no basis or bases of different cardinalities. So you might have coordinate systems where you need different numbers of coordinates for the same vectors. It seems totally nonsensical. And then some funny disasters in the real numbers. We saw this one already. A function can be sequentially continuous but not continuous. Complete subsets may not be closed. It's just outrageous. Subspaces of the reals may fail to be separable. These are all somewhat technical mathematical things that would offend you if you knew what they meant. And then infinite subsets may be Dedekind finite. It's very outrageous. So I'm sorry that I can't explain all of the technical conditions here, but I mean, I think at least they look, well, at least 1 and 4 look really bizarre. If there was interest, I'd love to explain exactly what's going on in all of these things.
Can you just go back to the Dedekind definition? So
Yeah,
if you
so-
have an infinite subset of R, and it's not, and it's definite, that means there's
So
no
it's
subset.
it's infinite in the normal sense,
Yeah.
right? It does not have a finite number of elements, so it's infinite.
Yeah.
But it's Dedekind finite because there is no bijection to a proper subset of itself.
Okay, so
So there's two different notions of infinite finite here, right? There's the D one, which is really identifying the finite ones, so the infinite ones. And the usual notion of infinite is defined by negation, it's by saying it's not finite. And then the Dedekind finite is saying that it's not Dedekind infinite. So bizarre things are happening here. I feel like I've lost many of you.
yeah, sure. So you're saying what is that of choice? The first example is the negation of choice, essentially equivalent.
Well, I mean, okay, yeah. So
So does that mean assuming
assuming the
choice is
negation
the
of
same?
choice, you must have at least one of these things. So,
But
when I say without choice, I mean if you. I mean without choice to be the opposite of having choice.
Yeah.
If you don't have choice, then there are models of set theory in which this is the case.
Yeah, so what you're saying is that your model does not have the axiom.
Yeah, if you don't have the axiom of choice, these things can happen.
Well, what you're saying is that without the axiom of choice, you have the negation of choice as a theorem, correct?
Well, no.
Isn't that what the first? Oh, I guess maybe they're not equivalent in this
I
model.
mean, I guess I should say that these things can happen. So if you want to be safe, say the negation of choice. You really need the negation to establish one. And probably all of these things fails. Okay, well, if you're really saying that these things fail, and that the products of non-empty sets is empty, then you want to assume the negation of choice. Or you can say without choice, there is some model of set theory satisfying these things.
Like, I guess the difference basically would be whether or not we can constructively find a set of non-empty sets whose product is empty. Because if we could find that, then we don't need the negation of choice. We just need not choice, and we construct it. No problem.
Since it's independent, you know that that won't happen kind of by accident. You will have to have it built into your model that these kind of crazy things can happen.
And if it's built into your model,
Then you might as well
basically have no choice.
Yeah, you basically assume the negation of choice.
Yeah.
Okay, so I think this ends my brief section on the crazy things that happen if you don't assume the axiom of choice. And I'm not sure that I've succeeded in convincing you that you should believe it, because I know a lot of these things are somewhat sophisticated mathematically. But this large body and this and several other more complicated results was enough to convince mainstream mathematicians that we should assume the axiom of choice. But unfortunately, with the axiom of choice come a whole bunch of crazy consequences that are some of the least intuitive things I have ever heard of. The first one, I think, is an answer to Aaron's question maybe a little bit. What's sometimes called the Hausdorff paradox. If there are subsets of real numbers or of the plane three-dimensional space, any kind of Euclidean space you like, that have no meaningful notion of length, area, or volume in the sense of this Lebesgue measure. There are non-measurable subsets. So we have, thanks to this guy, Henri Lebesgue, who we mentioned earlier, a really nice idea of how to define lengths of arbitrary subsets of the reals. Well, not arbitrary, unfortunately, but even pretty strange ones like the Cantor set and the rationals. So if you just look at the fractions amongst all of the decimal numbers, we can assign to that the length 0. That's pretty good because, normally we only know how to assign lengths to integrals, right? For all the numbers between 0 and 1, that seems like it should be of length 1. But you can extend this definition to really weird sets, like the Cantor set, which is this middle third excluded set, or just the collection of fractions. But if you do this with the axiom of choice, you can construct sets that have no meaningful notion of measure, or area, or length, or volume, which is unfortunate, because we would prefer, of course, every set to have this thing, right? So it's complicated because all of the results you state, you have to restrict this notion of length, or area, or volume to some weird subset of all the sets in which you are allowed to do these things. And then you have to consider the algebra of sets and what kind of operations am I allowed to do to these sets. It's just a massive headache. But maybe this is not such an offensive result. The next result is the really offensive result. One of my favorite results in mathematics, called the Banach-Tarski paradox. It's very old, from 1924. It says you can take a solid ball in 3 dimensions, decompose it into 5 pieces, and then reassemble those 5 pieces into 2 balls the same size as the original. And I have a very misleading picture of this, my only picture. So here is the ball. Here are, you only see 4 pieces. The 5th piece is actually only the center of the ball, so it's a single point. So you basically only need 4 pieces plus the center point, and then magically you reconstruct 2 balls the same size as the original. And this is misleading because these things look like wedges or chunks. Really, these pieces are kind of like clouds. Like you'll never get a handle on them.
Well, you can't get a handle on them because this is non-constructive
Because it's
mathematics.
non-constructive, yes. You're
If you could make
invoking
if you could draw a picture of it, then the
Yeah.
result would be false.
Yes, of course. So these sets are examples of these Hausdorff paradoxes. Obviously, there can be no meaningful notion of volume for these pieces, assuming volume is rotation and translation invariant. You think it should be. So I like to ask physicists how they reconcile this with what they do, right? The business of physics is using these mathematical results to describe the real world. Well, what do you do with this? This is the reason I try to involve myself in physics as little as possible. Physicists use the real numbers to model reality. And what do you do about this? I have no idea. Are there any physicists in the audience? I would love an answer to this question.
The answer is they ignore it.
I think, yeah, you have to, right? Maybe if you're into quantum physics, you can argue that space is fundamentally discrete because of this Planck length, and you don't have these issues.
Well, what
You're
happens in
subdividing
physics,
space.
in quantum physics, in relativity, you don't care because everything is too big to run into this problem. I mean, quantum mechanics, you basically run into weird paradoxes if you try to talk about physics that's smaller than the Planck length. So physicists just say, okay, we're not going to talk about things about smaller than the Planck length because laws of physics break down.
Sure.
And so then that's sort of like saying that space is like quantized,
discrete?
but not
Yeah.
exactly.
Obviously, the real answer is that physics is non-deterministic, and that is consistent with this.
Okay, sure.
I think the real answer is that most physicists do not learn the foundations of mathematics.
I imagine not. Yeah, you're probably the closest to an actual physicist. In the
Yeah,
audience.
I think of non-constructive mathematics as something that doesn't really apply to the universe that we live in. And I think of constructive mathematics as being like closer to a description of reality in some vague sense. But like I've thought about what would happen if matter was infinitely divisible and time was infinitely divisible, and then you could build a computer that could compute perform an infinite number of steps in a finite amount of time, and then all sorts of wonderful things become possible. But none of those are possible in the universe that we live in. It's just...
I certainly agree.
Yeah.
And so much of quantum physics is phrased in the language of functional analysis,
Yeah.
in which you use the axiom of choice all the time. Like I tell
Uh-huh.
people sometimes every 5 minutes, which is a joke in some sense. But you can do hardly anything without the axiom of choice.
If you're dealing with infinite things.
Well, you are, because like the observables to quantum physicists are operators on infinite dimensional Hilbert spaces. So and they're using choice all the time because like these brackets and things, these linear functionals, they use Hammond every day, and then this is equivalent, not equivalent, but a slightly weaker form of the axiom of choice. So
For space, you don't need the generality of Hammond, do you? I mean, you have the Greece representation.
yeah, so you don't. But
Explicit.
but if you're doing any kind of like non-Hilbert things like L1, L infinity examples, or any kind of
They don't need them for quantum mechanics, right?
I suppose not, yeah. So if you're happy living in this L2 world forever, maybe you can avoid it. But
And maybe L of L2 has problems.
I would imagine, yeah. So, I don't know, I've never been able to reconcile this anyway. We have to attract a physicist to this meeting so we can get to the bottom of it. Anyway, so I'd love to continue these philosophical discussions. I have one more slide. One of the weirdest, and I have to thank Aaron for drawing my attention to this. So other than the axiom of choice, the other non-constructive piece tool that mainstream mathematicians use today is this law of the excluded middle. And this says that for any statement P, either P or not P must be true. And this is the foundation of what's called proof by contradiction